Okay, let's look at another AC circuit problem here. And we're starting off with, again, it has C's, one inductor, two resistors. So it says find Z total. So we're gonna, again, it's just basically a series circuit if we combine these two in parallel, and we'll just have a bunch of elements in series. So let's do the combination stuff. Let's combine them as RLs and C's first, since the C's are already in parallel, and that's the easy one. And then we can convert. So if we combine these two in parallel, right, capacitors in parallel, they just add up. So the C total would just be negative J5. Oops, I'm sorry. Never mind. I made it hard on myself. They're already in ohms. And so to combine them in parallel, we have to do the 1 over 1 over stuff. So let's do that. So Z sub C is 1 over Z sub C total is 1 over negative J2 plus 1 over negative J3. Right? Capacitors always should have negative J kind of impedances. Inductors should always have positive J kind of impedances. Resistors should always have purely real, no J impedances. Okay, so if we combine those two, we have a J in the bottom of everything, so we can factor that out, and so everything will just come out to be multiplied by J. So we're just going to do 1 divided by, in parentheses, 1 divided by 2 plus 1 divided by 3. All right, so we get 1.2. So Z sub C, where do I want to write it? I guess just here. Z sub C total then is just negative J 1.2 ohms. Yes, okay. And so now, with Z sub C total being, say, make this into one capacitor, Z sub C total, now all of our elements are in series, so Z total is going to be Z sub C total plus Z of the inductor plus Z of resistor 1 plus Z of resistor 2, right? They're all just in series, so we just add them all up. So we're going to have negative J 1.2 plus, oh no, plus J5 plus 7 plus 1. Right, just going around here and adding up all those different Z's. So Z total is just 5 minus 1.2, 3.8, and 7 plus 1 is 8. So 8 minus, plus 8 plus J 3.8 ohms. So now we've combined all of those into one complex thing, Z total. So this has all the capacitors, inductors, and resistors in it. As far as the source is concerned, if we bring this source over here, it'll be 10 over square root of 2, angle of 0 degrees as a phasor, right? So 10 divided by square root 2, 7.07. For our source voltage in phasor world. Oh, and that's just what I was just going to ask. That's just what it asked next. So V sub S is going to be V peak over square root of 2, angle of phi sub V, whatever is in there, and like I just did, 10 square root of 2, angle 0 degrees, so 0.707, angle 0 degrees. Not 0.707, 7.07. Let's just write that over here to be a little neater. All right, so a very simple circuit. All it has is a source and a impedance. And so that's part B. That was part A. So part C says find the current. There's only one current. It's just a very simple circuit. And so we can say that Ohm's law still holds now. In phasor world, Ohm's law is V equals IZ instead of V equals IR. Instead of being VER, it's Viz now. And these are complex numbers. And so we can say that I then is V over Z. V is, there's only one voltage, right? The voltage of the source is the voltage across the Z. Right? Ohm's law only holds for Z's, right? And so we got 7.07 angle 0 degrees divided by Z total 8 plus J 3.8 ohms, volts. So we're going to get amps when we're done here. Okay, so how do we do this math? We could put in our calculator. 7 angle 0 is just 7, right? It's all just this way. Or we could do it with components, magnitude-wise and angle-wise. And so we could convert this into a polar form. And then we can do the cosines and sines stuff. Anyway, put it in polar form, and then we can use the equation for dealing with complex. When you're in polar form, dividing is just divide magnitudes and subtract angles. And so the Z total is 8 and then 3.8. So we can get this angle here, theta. Theta is 10 inverse of opposite over adjacent, 3.8 over 8. And this is kind of a general formula to get the angle of an impedance. Is inverse tangent of the imaginary part over the real part. And so imaginary part, if we have x's and l's combining, x's are positive, magnitude, this probably should be magnitude of x sub c, because x sub c are negative, and then we get, so that's the total 3.8 is the combination of x from the capacitor and the inductor. Anyway, so we can get theta here is inverse tangent of 3.8 divided by 8, 25.4 degrees. And so we could say then that I is 7.07 angle 0 divided by, well, now what's the magnitude? Well, that's the hypotenuse of the triangle, right? So we got to do magnitude of Z is square root of 3.8 squared plus 8 squared, right? So square root 3.8 squared plus 8 squared, 8.86. 8.86 at an angle of, what did I say, 25.4 degrees. All right, so when we divide complex numbers in polar form, just divide magnitudes. It's going to be 7.07 over 8.86. Angles, we subtract 0 minus 25.4 degrees. And so I is 7.07 divided by 8.86. 0.798 at an angle of negative 25.4 degrees. Amps. Right, if you have a smart calculator, you could just do it this way. You could do 7.07 divided by, in parentheses, 8 plus, and then get your I, however you get I times 3.8. And then it gives it to you in rectangular form. So 0.721. So it says it's 0.721 minus J.343 amps. All right, so it gives it to you in rectangular form, right? but we want polar form. Calculators do have a convert to polar kind of thing that can do it for you. And so it gives 0.798 and an angle of negative 25.4 degrees. Imagine that. Okay, or you could do the magnitude is the square root of 0.721 squared plus 0.343 negative technically squared. That makes this, and then the angle of I, phi sub I, is equal to tan inverse of negative 0.343 over 0.721. So you do need to be a little careful with which positive and which negative with the tan inverse stuff, but that should work. Tan inverse negative 0.343 divided by 0.721. Okay, what happened to my negative sign? Anyway, I lost my negative sign, but negative tangent is an odd function, so so the negative of an angle just makes a negative of the tangent kind of thing. All right, so we get the negative 25.4 degrees. However you like to do it, we won't have a whole lot of this. If you're uncomfortable with the math, you might want to just kind of use these equations, right? Get the total x, divide by the r, take a tan inverse, watch if it's going up or down. Remember x sub c, either, I need to fix this equation, this sheet here, this should be a plus. Well, x sub c, magnitude of x sub c is 1 over omega c, right? Positive, but in general, x z equals jx, and so the capacitors always have negative x, right? And so this is not, there wouldn't be double negatives. This negative is from this, so I should probably put magnitude of these on there in that equation sheet so that it makes more sense, okay? Because the capacitors have negative x, which x is called reactance, so have negative reactance. All right, where were we? So we found I as a phasor. Now we need I as a function of time. So real easy going from phasors to time domain. We just take the RMS times the peak, so times the square root of 2. We want the peak, 0.798 times the square root of 2. And we're using cosine for reference, so cosine 377t. And then we just add on the phase angle, but in this case it's a negative, so negative 25.4 degrees. Amps is our current in time domain. I of t. Find omega s for resonance. Resonance. Okay, so resonance, when we have a circuit like this that has capacitors that have negative jx stuff, and we have inductors that have positive jx stuff, if they cancel out exactly, right, it's almost like the resistor, or it's almost, in terms of looking at the total, those two are gone, right? All that's left is the resistor, right? Because Z total, if Z sub C is, negative J 100 and Z sub L is positive J 100, when we add this all up, right, those cancel out, and all we're left with is just the resistance is adding up. All right, so that's resonance. Resonance is when magnitude of X of L equals the magnitude of X of C. Right, and so they cancel each other out. In this example I just said they're both 100, but probably not. So what is omega S for resonance? So noticing, like we said in the equation sheet, the impedance of L's and C's depend on what the frequency of the circuit is. So now we're going to say frequency is not 377 anymore. We're going to find a different frequency. Maybe our source has it's a function generator, has a variable frequency. What frequency will make this resonance happen? All right, and so x of L magnitude equals this, so this means that omega L, or omega S for the resonant frequency, I guess, I don't know why S, but omega S times L, that's x of L, equals omega C, or magnitude of x of C, which is 1 over omega S times C. All right, so that gives us, just doing a little algebra, we get omega S squared equals 1 over LC, or omega S equals 1 over square root of LC, which is same as the natural frequency of the circuit when we were doing it in DC, right? You saw that omega we have on our equation sheet. You can kind of take this as both the equation for the natural frequency when there's just L's and C's and they're oscillating with each other and no source, or this is also the resonant frequency. All right, so that's 1 over square root of L. This is all total stuff. L total. Okay, that's a problem. I didn't give us L total. What is L? So we have omega L. We have Z was given as omega L was 5, right? And we know that omega in that case was 377. So L then is 5 over 377. So 5 divided by 377 gives us the actual L. 13.3 millihenries. Okay. Magnitude of Z for the inductor, or X for the inductor, is just omega L, just like I was saying up here. And so we're going to have 13.3 times 10 to the negative 3 for L here. And then 1 over omega C total, we got 1.2. Oh, is this the one? .2. Again, omega was 377 before, and so C total is 1 over 1.2 times 377, if I did my algebra right. Bring that out, bring this in. 1 divided by, in parentheses, 377 times 1.2. 2.21 millifarads. All right, so we have in here for C 2.21 times 10 to the negative 3. All right, so 1 divided by square root of 13.3 e negative 3 times 2.21 e negative 3. 184. 184 what? Omega radians per second. Everything is in the correct units. It should be in the correct units. So the resonant frequency, the frequency for resonance, oh, this is omega source. So this is what the source frequency would have to be. That's why I called it S. So omega S, to get the circuit to be in resonance, to make the inductor and capacitor cancel each other out, omega S, 184 radians per second. All right, so if the source had that frequency, it would make the total impedance be the smallest it could be, because all the imaginary stuff goes away. All you have is a resistor, and so the resistance, and so the resistors you can't get to go away. But if we had a very small resistance in the circuit, it could almost make the impedance go away, and so that would make what would that do to the current? If you made Z be very small, that gives us the maximum current. So at our resonant frequency, we get a maximum current for this given condition. And let's just forget this one. Find the new L and C to get resonance at 60 hertz. We would just use this formula and put in 60 hertz instead to get L and C, and we could add in this is just saying, you know, whichever one needs to be added to, we would add that to it. So let's just skip that. We get the idea here. The only one thing that we could gain from that experience, I guess I would say, let's just put in here a new E. What is F at resonance? All right, so what is F for this omega S? Well, omega is 2 pi F, so F is omega over 2 pi. So divide this 184 divided by 2 pi. Is 29.3 hertz. By the way, what was the 377? If you have omega is 377, like our initial circuit here, omega was 377, that is F equals 60 hertz. That's the normal AC frequency in the United States. Okay, we'll stop there. Maybe, if I can get this thing to stop.